I want to talk about the Class B AB amplifier from section 10-7 in your text. And I'm going to use figure 1043. This is out of the problem sets in the back of the chapter. And I think that this figure is used for questions 1029 to 1033. So it's a good example. I'm going to use it to explain a couple of things here. So number one, if you're looking at this diagram, I want you to take a look at the front end here. There's a CE amplifier, there's a preamp. There's a preamp at the front of this. I'm not going to talk about that here. I'm going to do that in a separate video. I want to focus on the A/AB amplifier. So don't worry about this for now. I will say that it has a fairly large gain, and that's something to keep in mind. So on the BAB amplifier, one of the first things that you should notice is that this is not a split supply. This amplifier has 30 volts, it's a single supply, and the power supply is 30 volts to ground. That's no problem, you can totally do that. The only thing that you have to keep in mind is that when this was plus minus 15, the point here in the middle was 0 volts. It's no longer 0 volts, but it's still halfway. It's halfway between 30 volts and ground. So this point here in the middle, it's going to normally sit at 15 volts, the halfway point. And so is this point between the diodes. This is going to be halfway. It's going to be sitting at 15 volts. Now, in order to ensure it's 15 volts, when you bias this thing here, you pick a couple of resistors that kind of gets it close, but you put a variable resistor in here with a trim pot and you turn the screw until that point is exactly 15 volts. So the exact values of beta and the resistors aren't that critical on this, and even doing the DC analysis really isn't that critical as long as you're close, as long as this resistor here is big enough that you can dial in that this point, you need this point to be 15 volts. As long as you can get that, you're good. Now, you don't really have to do the DC analysis, and I've said that a couple times, and here's why. If this point is sitting at 15, then this point here is 0.7 volts less than that, and this point right here, the base voltage here, it's 0.7 volts above that. That means that across R7 here, you have 14.3 volts. And with that number, now that you know what the voltage across that resistor is, you can figure out what the current through this resistor is. So I can figure out the current through this, and that would be IC, which is approximately IE, which is approximately 14.3 volts over the collector resistor, which is 1K, so it's 14.3 milliamps. That's really close enough to be able to go ahead and do your AC analysis. I'm going to say that IE is about 14.3 milliamps. So let's zoom out here. Let's zoom out and take a look at the DC analysis. And I have that here. So the DC analysis, same process as you're doing with the other amplifiers. You draw the AC equivalent circuit. You draw the AC equivalent circuit over here. You take each part, you look at each part on the original schematic, and you transfer it over. That 12K goes over here to ground. This 1K goes up here to ground. Put a box in for Q2, the transistor. Off the emitter of Q2 is this 100 ohm resistor. And then off the collector, we have RC, which is 1K. The diodes we think of as a 0.7 volt DC drop. So when we go to the AC equivalent circuit, they are shorts. So they are gone from here. Now that I've got the AC equivalent circuit, I can go ahead here and I can figure out my important characteristics. So as I said, R prime E, 25 millivolts over 14.3 milliamps. So about 1.75 ohms. Put that in there. Zin would be this, parallel with this, parallel with this. So our 12K, parallel with 1K, parallel with 101.75 times beta plus 1, worked it out to 871 ohms. Zout is the impedance looking back from the load. So Zout you would say is basically RC, that's 1K. The gain, Vout over Vin. So for Vout over Vin, what I would do is I would identify those 2 points first. So I would draw a little line that says, okay, this piece of wire here, this is Vout, and the current goes back and forth between collector and emitter, and the current goes through RC. So I would say Vout, which is the voltage across this guy, that's going to be IC times RC. The collector current, it's going to be the collector current going back and forth through this resistor. So that gets you Vout. Vin now, Vin is this piece of wire here. This is all Vn, and I would say that Vn is equal to IE, that's this current, times these resistances. So Vn is IE times R prime E plus RE. Now the IC over IE, this thing here is pretty much 1 if beta is any significant value. So we can say it's approximately this. And then when I put numbers in for it, I get 1000 over 101.75. Gain is minus 9.8. So that's this section here taken down to its characteristic values. So let's put those numbers. I believe this was 891, 871. $871 minus 9.8, and Zout is 1K. Now there's, in the examples we've done in the past, I've usually said draw these as turn this section into a 2-port model, like so. And then take this section here. Usually you say, okay, turn this one also into a 2-port model. But I'm going to show you something that happens when you do that with these direct connected amplifiers. So if I say the first stage, the Zout is 1K. If I look into the base of the transistor for the second stage, I would say that there's going to be an R prime E there. I would say that Zin is these two guys, mostly RL. So Zin of this stage is mostly RL. So stage two sees pretty much RL as its Zin. Then I would figure out the gain. I'd figure out the gain of the common collector amplifier, which we know is about 1, so this is 1 times Vn, and it's positive. And then I would take a look at the Zout. I would stand here at the load, and I would say Zout for this circuit would be, I'd look back through here, and I'd say, oh, there's R prime E, and then there's this thing divided by beta, so it would end up being Zout looking back from the load would be R7 or RC over beta plus 1 plus R prime E, which is 1K over 151. That's 8.4 ohms. So I would put that down here. And this is 1K ohm. Here's the problem with this approach. This Zout is essentially and when I say by essentially, I mean it's driven a lot by the 1K over the 151. So this Z out is from RC. Well, this Z out over here is also RC. Here's the load resistor, which is 100 ohms. And over here, this is Z in. So that's looking this way. This is primarily RL. So this Z in is pretty much RL. And this load is pretty much RL. This Z out is pretty much RC. And this Z out is pretty much RC. So if you look close, what you might recognize is that, hey, here's a voltage divider between RC and RL. This is RL over RL plus RC plus RL. And this voltage divider is also RC over RC plus RL. So that voltage divider is in there twice. And that is an error. That's a problem with this this analysis method. So you don't want to do that. What you want to do in order to avoid that is you want that voltage divider on there once. So I would get rid of this second amplifier, and I would stick the load right on here. And then I would stand at this point and I'd look back into the circuit, and I would say that Z out is 8.4 ohms. And I would say that the gain here is the minus 9.8 times the 0.98, the typical Cc amplifier gain of 1. So I would say it's minus 9.8. So I would model the Cc amplifier. I would look here and I would find Z in 871. I would look here and I would find Z out, and I would put that here at 8.4 ohms. And then for the gain, I would take the gain of this circuit here and I would multiply it by the gain of this circuit and can treat them as one dependent voltage source, and that would get me approximately minus 9.8. And this is your final model of this part here. The Class A, Class B AB amplifier. So there you go. This represents the CE amplifier and the push-pull amplifier as one model.